Hello, everybody. How you all doing today? I apologize in advance. I've got a bit of a cough, so if I'm coughing during the lecture, that's all I can do. So welcome back to Computer Science 3200. I've got the right spreadsheet open here. Yep. So today we are talking about bandit algorithms. So last time we talked about an introduction to sort of what reinforcement learning is. And today we're going to start our actual, how do we start to represent things? How do we hold our beliefs of things? How do we learn over time? And we're going to start with the concept of bandit algorithms. So let's jump right into it. So lecture number 14, we're going to talk about exploitation versus exploration. These terms, I can reverse them. Sometimes I say exploration versus exploitation, and also bandit algorithms. So last lecture, we ended off with this slide, which was that one of the main challenges in reinforcement learning is the trade-off between exploitation and exploration. To obtain a lot of reward, agents must prefer actions that know good results, so that's exploitation. But in order to learn which actions produce good results, it must try them out first, and that's exploration. And so you have to exploit knowledge that you have, but also explore in order to gain more knowledge. And I said that this is one of the main challenges in real life, and a good example of this in real life would be like eating at a restaurant, right? Deciding where you want to eat tonight. So you're going to exploit the fact that there may be a particular restaurant that you know is pretty good. So maybe you'll go there because you know what to expect. But maybe sometimes you also want to explore and try a new restaurant because it might have really good food that you'll go to more often. And so that's sort of the whole exploitation versus exploration thing. And we have to mathematically tackle that some way when it comes to reinforcement learning. So we talked a lot about reinforcement learning, but what is learning, I guess, is a good question before we talk about reinforcement learning. So learning, one definition, might be the process of gaining new knowledge or modifying existing knowledge. So, for example, the stove was hot the last time I touched it. If the stove is red, don't touch it. That's good new knowledge. So we have learned something if we have information that we didn't have before. That's good. But also, even if we do something for a second time and we get the exact same results, we have still learned something. Because what that means is we are learning to trust those results with more certainty. And you'll see I will have very well illustrated examples of this in this lecture. So our estimate is going to have less variance over time. So for example, if I choose door number 3, and I get 100 gold pieces in my video game, if next time I choose door number 3, I get 100 gold pieces, then even though I got the same thing and nothing new happened, even the fact that nothing new happened is information, right? I am more certain that next time I'll also get 100 gold pieces. So exploitation is exploiting our current knowledge. And it means that we are going to choose a high-valued action for which we already know the value. So I'm going to go to Wendy's. I'm going to get a junior bacon cheeseburger because that's a pretty high-valued action, especially when you divide it by the price, right? So the utility of a junior bacon cheeseburger is very high for me. Exploitation is low risk and possibly low reward. We know what we're going to get, right? So always choosing actions we are familiar with doesn't give us as much information as if we try new actions. So new actions is exploration. This is just a little gif of a plane here my face is covering up. So let's try actions that we haven't tried before, or we're going to try actions that we have tried before that we are uncertain of. So it helps us to learn their true values. So it's possible that new actions are going to have higher rewards than previously selected, right? But once we have explored sufficiently, then we can exploit the best actions and know that theirs the best. Someone just made a Wendy's comment in the chat, so I have to respond to that. The Dave's single is only $4 right now. So I'm not trying to advertise for Wendy's. I actually, on Monday, or I guess that's yesterday. That is exactly what I had for lunch. I had the Dave Single combo. So you're speaking my language. Okay. So here's a great example. This is like the canonical example of exploration versus exploitation. And it is called the N-armed bandit problem. So down here, we have got an octopus pulling slot machine levers. So we are repeatedly going to make a choice between n different actions, n being the number of actions that we can choose between. After each action, you're going to receive a reward from a stationary probability distribution depending on the action. And we'll talk about what stationary probability distribution means in a couple of slides. Your objective is to maximize your expected total reward over a number of action selections. So, okay, that's a mathematical definition. What does this mean in practice? So if you have a bunch of slot machines in front of you, and I'm going to repeat this a little bit later, let's say you have 5 different slot machines in front of you, and each of those slot machines is going to have a different return on investment. Maybe one of them always wins, one of them always loses, one of them always gives you half your money back, right? But you don't know which one is which until you start trying. So if I give you $100 and I tell you, go maximize your profits, what is the algorithm that you will use to make those selections? Okay, that is the N-armed bandit problem. It's also called the multi-armed bandit problem, and the name is an analogy to slot machines. So slot machines, at least the old ones, used to have to pull a lever to get it to work, right? That's because it was a mechanical device, and that is, it has one arm, and it's a bandit because it's stealing money from you, right? Like, slot machines are not a profitable venture, and so they're called one-armed bandit. If you have many slot machines, then you have the multi-armed bandit. So you have a limited amount of money, and you're trying to win as much money as possible. So how do we select which levers to pull? And it turns out that the N-armed bandit problem is everywhere, right? We've got choices in life. We got going to restaurants. That's an N-armed bandit problem. We've got some pathfinding that we're going to do in assignment 5. That's an N-armed bandit problem. So exploitation versus exploration. I've had like hiccups all day. Excuse me. If we maintain an estimate of action values, right, and we'll talk about that, what that is in a second, but if we have some data structure keeping track of like which slot machine I think is the best, then at some point in time, there is a value that's the biggest, right? And so if we have current estimates of all the possible action values, the best one is called the greedy action. Okay, that's the greedy action is choosing the action that I currently think has the best value. So exploitation is choosing the greedy action, and it maximizes single action returns, right? So if I've, say, averaged all the returns from the slot machines, and this one has the highest value, taking the greedy action is selecting that one with the highest average, for example. Exploration is when we choose a non-greedy action to improve our action estimates. And this is required for future reward maximization, right? Because we want to know, out of everything, what has the highest eventual reward. And the whole idea here is, how do we balance exploration versus exploitation? So you could just say, okay, pull all the levers 1,000,000 times, right? And after we pull them all 1,000,000 times, we have a pretty good guess at what the best action should be. But like I said before, if you are going to the slot machines and you only have $100, then, you know, you can't pull all the levers 1,000,000 times. So you're typically going to have some sort of budget or time limit or learning limit or whatever that makes you want to do this as fast as possible. So how are you going to balance exploiting knowledge that you have versus exploring new actions? Well, so there's 2 important concepts when it comes to exploration versus exploitation, EVE, and this is how we actually implement things, okay? So the first concept when it comes to actually like mathematically implementing things is, first is, how do we store and update value estimates as we learn over time with new information. So for example, if we have 10 slot machines, do we have an array of size 10? Maybe that's a good idea, something like that. And then the second thing is, how do we choose which action to do next based on our current value estimates, right? So we have some estimates, which action do I choose? So it's basically going to be, I have a current, I'm going to store my current values. Based on those, I'm going to make an action. I'll take the action, then I'll update my values to reflect mathematically whatever happened on the last pull, and then this cycle will repeat. So action value methods. How do we store the current value estimates? Well, we're going to have a mathematical representation for that, and that is Q. So QT of A is our estimate of Q star of A after time step T. So what the hell is Q star of A? Q star of A is the actual value of an action A, meaning the average or the mean reward, right? So for example, if we had infinite pulls of a slot machine, or we had the source code of the slot machine, we might be able to say, okay, this is going to give us half of our money back. So Q star of A, if it gives us half of our money back, is going to be equal to 0.5 or some equivalent like that. So how we are storing our current estimates is that there's going to be some number of time steps, meaning maybe T represents how many times we've pulled the levers. And our estimate after that many pulls of a given action is going to be the estimate of the true value, which is the thing we're trying to figure out, right? All we can ever do is estimate unless, someone hands us the source code to the slot machine, which they're probably not going to do. So how do we actually implement this Q value estimate? Well, here's an example. If we have the n-armed bandit problem, Q of A is going to be the estimate of bandit A's reward. So choosing a bandit is one action. So for example, let's just have an array of size n. And so we're going to have n equal to 4 maybe. So we have four slot machines that we're using. Q0, because it's time step 0, I haven't done anything yet. I'm going to choose some initial values, so maybe they're all 0. And then after some number of time steps, maybe I have some other estimate of what I've done so far. I've gotten a bunch of numbers, and this is now what I believe the values of those things are, right? So let's step through an example, and this example is going to be, let's step through an example now, and this example is probably going to be related to an exam in some way, shape, or form. So make sure you know how to do this example. So here we go. I spent a bunch of time on these slides, so let's get it right. So here, I've got up here, sorry, my face is hiding the number 4 up there. So it's not hiding anything else, it's just the number 4. So I can leave the camera up, that's good. So on the top here, I've got my different bandits. So I've got all my slot machines 1, 2, 3, and 4. And so N is 4 this is the 4-armed bandit problem. And so these are my actions. So A equal to 1 means I chose the first slot machine. A equal to 2 means I chose the second slot machine. Okay. My distribution, we'll talk about that in a second, but this will be my distribution. This will be a list of all the rewards I've gotten if I have selected that slot machine. And down here, I am storing my values. Okay, so at some time step T, this is going to be QT of 1, meaning my estimate after T time steps of action 1, 2, 3, and 4. So that is what this diagram means. So the first thing we're going to look at is the distribution. The distribution means essentially what is the function that is returning rewards from these slot machines. They could be completely different, right? So, for example, I've made up some sample distributions here. So this slot machine, if I pull that lever, it's always going to give me 5. Okay? It's a pretty weird slot machine, but it's always going to give me 5. This one is either going to give me negative 20 or positive 20. Okay? This one is going to give me a random number between 0 and 10. And this one over here is going to give me a random number between negative 10 and 10. So if you're out there in the chat right now, tell me which one of these you would want to pull and why? Which one would you choose right now if you were given the distribution? Okay, so just think about that. Some people said 1, some people said 3. All right, let's see. Okay, that's great. So we got a lot of people saying 1, a lot of people saying 3. All right, so you're probably thinking in your head now that we should probably be thinking about an average, right? What is the average return here? So let's get to that. Now, keep in mind that when we are doing reinforcement learning or Bandit algorithms in general, we are not given this distribution. Because if I was given this distribution, I could easily work out the mathematics, right? I could say, okay, the average here is 5, the average here is 0, the average here is 5, the average here is 0. So pulling 1 or pulling 3 in the long run is going to make me the most money. Maybe in the short term, if I want to take a big risk, I could pull this one, right? But probably not going to pull this one. So if I'm given the source code, if I'm given the distribution, I can sort of mathematically know what Q star of A actually is, right? Because this is Q star of A. It's 5, it's 0, it's 5, it's 0. But I don't know that. I'm just listing it here for the slides. Second, how am I going to choose my Q0 for each of these things? At the very beginning, when I start playing all these slot machines, I have to have some initial guess, right? So there's essentially 2 trains of thought here. One is that you start at 0, or if you have some other information, you could start with that information, right? So we're just going to start at 0. So our Q0 for action 1, Q0 again, meaning before we pull any actions, Q0 of 3, Q0 of 4, we're just going to set those all to 0. Okay, now we are ready to start playing this game. Okay, I lied. We're not ready yet. There's 2 main variants of keeping track and updating our estimates of values that we're going to look at. The first one is called sample average estimate, and the second one is called incremental update estimate. So, what is this first one? The sample average estimation. Well, the natural way of calculating QT of A is to average the rewards seen so far after some number of plays, right? So if at play T, action A has been chosen KA times, yielding rewards R1 through R2 up to RK, then we just have QT of A is equal to the sum of all the rewards divided by KA. So I know that formulas can be scary sometimes, but this is dead simple. It just says add up all the things you got from the slot machine and divide it by the number of times you played the slot machine. It's literal definition of average. So if KA is 0, then we have to just define it as some default, and what we've done is we've called it 0. And so the idea here is that as KA gets really, really large, that is the number of times we have chosen that slot machine, QT of A is going to converge to Q star of A. And that just means that, you know, if we play the slot machine infinity times, then we've estimated the actual average, right? So the more times we choose it, the more certain we get about its value. And so if we take the average of the samples, then this is the sample average method. So let's have a look at the sample average method. All right. So what we're going to do is initially we're just going to pull left to right. Okay, we're going to pull each slot machine twice, and we're just going to go left to right. We're not going to talk about how we choose our actions yet. So let's say that we are going to pull slot machine 1 and we get some reward. So we got the reward of 5, right? Because this one is always 5. So how do we update our value here? Well, we just use the average formula. We're going to sum up all the rewards. So the sum of the rewards is 5. And we divide that by the number of times we've played this slot machine. And since we only have 1 reward, we've only played it once, so it's 5 divided by 1, which is 5. Pretty easy. We pull this slot machine next, and we happen to get minus 20, right? So we get minus 20 divided by 1, we get our minus 20. Then we pull this one, let's say we get a 4. So now 4 divided by 1 is 4. Now we use this one. Oh, we get an 8. So 8 divided by 1 is 8, right? So you can see here that after one play of each slot machine, we think that this one, our belief of this one is 5, our belief of this one is minus 20, our belief of this one is 4, and our belief of this one is 8, right? But we know from our analysis of this that these values are way off because we could have gotten lucky or unlucky on our first throw, on our second throw. But if we keep doing this, as t approaches infinity, these values will converge to the true values of the slot machines. So let's keep going. We're going to pull this one again. Well, it always gives 5, so that's a really easy update. 5 plus 5 is 10, divided by 2 is 5. If we pull this one, and we got 20, now we've got negative 20 plus 20 is 0, divided by 2 is 0. And this is Q6, right? So Q6 of 2 is 0, because we've done 6 total actions so far. Now Q7, we get a 0 here, so we got unlucky with that pull. So 4 plus 0, that's 4, divided by 2 is 2. And for our last one, maybe we got a negative 2 with this pull, and so we've got 8 plus 2 is, or minus 2 is 6, divided by 2 is 3. So we just keep going on and on and on with that. So on an exam, I could give you these numbers and you could very easily calculate something like this, okay? So that's it. That's the sample average estimate. You're taking samples, you're pulling slot machines, you are getting the rewards from them, and you are summing the rewards, dividing by the number of total tries of that slot machine, and that is your estimate. That is, at the end here, Q8 is equal, Q8 of 1 is 5, Q8 of 2 is 0, Q8 of 3 is 2, and Q8 of 4 is 3. Okay, the next way of doing things is the incremental update estimation. So here's the thing about this method. Let's say we are actually in a computer and we are trying to play this game billions and billions of training steps, right? We get billions and billions of samples. Well, we don't want to have to store gigabytes and gigabytes of data of every reward that we've ever gotten, right? So how could we, instead of keeping a list of all the rewards and summing that up every time and dividing that by the average, how could I get a formula that could take maybe the previous answer and the new answer and come up with a new update? So if we recall, our previous calculation for QT of A, as I just said, involves summing all the rewards and then dividing that by the number of times we pulled a slot machine. The problem here is we need to store all the rewards, and that can get very cumbersome. And the problem there, the main problem, is that the memory and computational requirements go over time. So if we're doing the first action, that's going to be almost instantaneous, but the millionth action, we're going to be adding up a million things, right? And so we don't want this to get slower and slower over time. So let's derive an incremental formula so that memory is no longer an issue. So what we have right now is that the new average, so our new Q value, is a function of the history of all the samples, right? So we need to know all the samples currently in order to get the new update. But what we want is, or what is wanted, is that the new average instead is a function of simply the old average and the new sample. So we shouldn't have to store all the samples. That's called the incremental average. So let's derive that now. Here's our function that we had before. So QK is equal to the sum of all the rewards divided by K. If we turn this into the summation formula, we have QK is equal to 1 divided by K and the sum from I equal 1 to K of reward I, right? That's pretty easy so far. So given that this is the formula, let's figure out the formula for QK plus 1. Well, if we just sub in K plus 1 for K, this is the formula for QK plus 1. And if we look, this is exactly what we've been doing so far. But let's play around with the math here. And what we're going to try and do is derive a formula so that QK plus 1, instead of being dependent on this huge summation, meaning we have to store all the rewards, we're going to try and get QK over here on this side. Let's see if we can do that. So let's expand this a little bit. So what we're going to do is right now on this line, we're summing from I equals 1 to k plus 1. But what we're going to do is we're going to take the k plus 1 term out of this summation and just put it on its own. So we've taken our k plus 1 and put it on its own, and now we've got the summation from I equal 1 to k. So you can kind of see where we're going with this now. So if this is true, then this is equal to, right here, that right there is equal to this, but divided by k, right? So this is equal to, if this divided by k is equal to qk, then this is equal to k times qk. See how that works? So just pause that for a second until you understand that step, because that's a little bit important. This right here, this term, the summation of I equal 1 to k of ri, we saw that right here. But if we take this k and we move this over here, right, because we can multiply it by both sides, then we get k times qk. And we've eliminated the summation from our formula. So now what we're going to do is we are going to do some little trickery. So what we're going to do is we're going to take this, we're going to add qk and subtract qk. So in what we've really done here is nothing, right? Because we've just added something and removed it, but it's going to allow us to do a little bit of factoring here. So what we now have is if we have k of qk and another qk, then we have k plus 1 times qk, then we can factor that in. And now we're subtracting qk, and watch what we can do now. We can pull qk outside of here, and then what we have is 1 over k plus 1 times our k plus 1 minus qk. So what does this mean? Well, it means that the average on the next time step is equal to the previous average plus 1 divided by k plus 1 times the new reward minus the old average. So look at that. We've got a formula now to be able to update the average, and all we need to keep is the old average and the k value. That's it. So that's pretty cool, I think. We don't need to sum all these values anymore. So if qk is the average of the first k rewards, and that's what we had, then qk plus 1 is equal to this, which is equal to what we just derived. And so what we have here is the new estimate, qk plus 1, equals the old estimate, qk, plus this term right here is called a step size. We'll talk about that in a bit. And that is the new sample times the new sample minus the old estimate. So the new sample is referred to as the target value, this new sample here. It means the target value is what we want to update our estimate to more closely reflect. So for example, if we got a sample of 100, 100 is our new sample. So that is the target. So we want to move our estimate toward 100 by some value. Okay, so that's the formula. And the reason why we want to change, or how am I going to phrase this? Okay, so this is the sample incremental update for the average of something. Okay, so this is how you would figure out the average without that big summation. Now, averages work fine if your distributions never change. Okay, so let's take this into account. Let's say we've pulled all of these slot machines 1,000,000 times, right? So we've got a bunch of money or very little money, but we've pulled all of these slot machines 1,000,000 times. Once I've pulled them 1,000,000 times, I am very certain about the average. I am so certain I could probably tell you exactly what the slot machine is going to do on average, right? But what if after 1,000,000 pulls of each slot machine, there's like a patch on the slot machine server and they update the distribution? So now instead of always being 5, it's always minus 20. right? So I start getting some minus 20s. But since I have a million samples at 5, and I'm very sure that it's 5, if all I'm doing is updating the average with these new minus 20s or minus 100s, then my overall average is really not changing that much, right? So just think about it if you were doing this. So if you had pulled something a million times and it always gave you a 5, and you're like, I am very certain that it is a 5, but then it gave you like 3 minus 100s in a row, wouldn't you think something was up and like probably trust that, okay, this should probably go more towards minus 100, right? My value of this should be moving toward that. But if I've got 5 million as my current sum, but now my sum is only 5 million minus 100, then my new average is going to be like 4.999999 or something. Versus I should probably be paying attention to these hundreds. So this is called a non-static distribution, where the distribution that is controlling the slot machine is changing over time. And this can happen in the real world. So, changing reward distributions. If the distributions remain the same, then the problem is called stationary. Okay? The distributions are stationary. If the distributions are allowed to change over time, it is non-stationary. So imagine having an average of 1 for a million time steps and then changing to 100. The average update would be really, really slow. So one example that we're going to do in the assignment, so in assignment 5, is for pathfinding using reinforcement learning. And so if you're really, really sure over a long time, if you're just taking averages and you find this like average best path, but then someone puts a wall where your previous best path was, well, you probably shouldn't be running into the wall for a long time, right? You should be recognizing that something is different. So for non-stationary problems, averaging works fine for stationary rewards, but not if it changes over time. So what we want to do is with an average, every single sample that we've ever taken is given an equal weight, right? So the very first thing that I ever saw is worth just as much as the most recent thing that I saw. What we kind of want is to weight recent rewards as having more trust than older ones, just in case the values change. And so what we can do is we can use this step size parameter, and I'm calling this thing alpha. So instead of having 1 over k plus 1 here, we just have this alpha. And it's going to be very obvious what this alpha does after I show you some examples. So this is our new incremental update rule. It's that our new sample, our new estimate is equal to the old estimate plus alpha times the new reward minus the old estimate. This is kind of hard to visualize, and I'd be very surprised if you're able to visualize it yet, but I have a diagram which is about to come up and it'll just click and you'll be like, oh, that's really interesting. So in order to start to visualize this, our new estimate is pulled toward the last sample by alpha. What does that mean? Let's have a look at a numerical example. If our current estimate is 50, right? So our current estimate is 50 and our alpha is equal to 1. So alpha is between 0 and 1. If alpha is equal to 1 and we get a new sample of 100, okay? So our current belief is 50. Our new sample that we just got is 100. Alpha equal to 1 is going to mean that we 100% trust the new sample only. And here's how the math works out. So we have our previous sample. We're going to add 1 times the new sample, which is 100, minus 50. So we get 50 plus 50, which is equal to 100. If, however, our alpha was 0.5 instead of 1, then what we're actually doing is moving halfway from our old estimate to our new estimate. So let's think about that intuitively. If I get 100 and I had 50, what is halfway between 50 and 100? It's 75. Let's see if the math works out. 50 plus a half times 100 minus 50 is 75. So this is exactly what's happening here. Here's the first case where we had alpha equal to 1. So let's say we're just visualizing this now. It's the same math, but let's say we have a number line down here. So our current estimate of QK is 50, right? So currently thinking 50. Our new sample is RK plus 1, right? That is our new sample. What alpha does is you can think of alpha as literally dragging us toward the new sample. So if alpha is equal to 1, we are going to completely trust the new sample, and our new belief will be 100. If alpha is 0, we don't trust the new sample at all, and we continue to believe that it's 50. So here's the example where alpha is equal to 1, right? So 50, let's look at these individual terms. This term right here, RK plus 1 minus QK, what is that? Well, that is the new sample minus the previous sample. So it's the difference between my new sample and my previous estimate. Okay, it's the difference between what we just saw and what we previously believed. That's what that is right here. And now this is saying, okay, scale that difference by alpha and then add it to our previous estimate. So if alpha is 1, then we take the difference and we add that whole difference to our previous estimate. And so now our QK plus 1 would be all the way toward 100. But if our alpha is 0.5, right, and our new estimate is K plus 1, then alpha here, we're going to go half this distance between the current estimate and the new sample. So that means that our new K plus 1 is going to be 75. Okay? And the cool thing about this is that you can play with that alpha value, and if the distributions change over time, this will help you to believe those more recent samples more than the old samples, which may be out of date. So let's have a look at that exact same thing we did before, but now we're using the incremental update. If you look up top here, we're using incremental update with alpha equal to 0.5. So if I say on an exam, here are some samples, and update your beliefs with the incremental update with alpha equal to 0.5, you should be able to regurgitate this example, okay? So like before, we are going to take a sample here. Our Q values are listed down here. They are currently 0. So if our previous value was 0 and we got a 5, then we are updating our value to be halfway between 0 and 5, which is 2.5. Okay? If we get a negative 20 here, then we are going, we got a negative 20. So now we are going halfway between 0 and negative 20 is negative 10. We get a 4 over here. Halfway between 0 and 4 is 2. We get an 8 here. Halfway between 0 and 8 is 4. Now things start to get interesting. We get another 5 over here. So now our calculation is moving our belief to be halfway between 2.5 and 5, which is 3.75. Okay. Now if we get a 20 here, then our value update is between halfway from negative 10 to 20, which is actually 5. And you see how this works? If we had just been doing the average, then negative 20 and 20, we'd have 0 down here. But we are trusting the most recent samples a little bit more. That's what this alpha update is doing for us. So we've got a slightly positive value rather than a 0. Now I'm going to get a 0 here. So I have to go halfway between 2 and 0, which is 1. Over here now, I'm going to get negative 2, which is going to bring me halfway between 4 and negative 2, which will be 1. All right? So after 8 time steps with the incremental update rule, after 8 time steps with the incremental update rule, here are our values, right? But here is what they were when we used the average. So the values are a little bit different. but they are both going to converge eventually to the correct values. It's just that we didn't do many samples here, okay? All right, that's like how we update our values, but now how do we actually select our actions? So once we have values or estimates of values, how do we select actions based on those? So for example, if we have these current values, which action do we choose? And you might just say, well, choose the highest one. Well, that's called greedy action selection. So how do we select an action from our value estimates? The simplest way is called greedy selection. On play t, at time step t, choose a greedy action. We're going to call that A star. Oh, geez. A star, this is not the A star search algorithm. We're just calling it A star, for which QT of A star is equal to the maximum A of QT of A. Well, what the hell does this mean? It just means on time step t, look at the values for all of our actions and choose the action A that maximizes that value. And then, and so this is, that's the value that we want to choose, or the value of the thing that we will choose. So look over all of the actions, choose the action which maximizes that, and that's the maximum value, and we take that action. So this method always exploits current knowledge to maximize immediate reward. No sampling or exploration to determine values of another action to see if they may do better. But here's the problem with greedy action selection, right? Let's say we had all zeros down here, and then we chose something. If that value is bigger than our initial estimate, so we initially guessed zeros, now we got a 5, it's just going to choose this 5 forever, right? We will never do any exploration. And so the problem is, if you choose greedy, then you will do 0 exploration, and you'll end up probably just picking the same thing from here on and never doing anything any better. So there are many ways to solve this, but what we want to do is, instead of just choosing greedy, we want to add some exploration somehow, right? So choose this one some of the time, choose that one some of the time, try something new every now and then. The easiest way to do that is called epsilon greedy selection. So the simplest way to add exploration is just choose a random action with some probability epsilon. So in the limit, meaning as time goes on, if we're choosing random actions sometimes, as the number of plays increase, each action will be sampled infinite times. So this is going to guarantee that as Ka, which is the number of times you've chosen an action, goes to infinity, Qt of A, which is your estimate of the value of A, converges to the actual estimate of A, or the actual value of A. So in theory, this works, but in practice, depending on the value of epsilon, it may take a long time to converge. So what's going to happen is, if epsilon is, say, 5%, right? 5% of the time, we're going to choose a random action. But 95% of the time, we're going to choose the greedy action. So if we have epsilon greedy action selection, I'm repeating, a random, so again, 5%, so that's epsilon. 5% of the time, we choose a random action, and we choose the greedy action, 1 minus epsilon, so 1 minus 5% is 95%. 95% of the time, we are going to choose the greedy action. So in general, I want to show this graph, because let's talk about what epsilon actually does. If epsilon is 0, then we are never exploring, right? If epsilon is very high, we are only doing random actions. If epsilon is somewhere between, then sometimes we're doing greedy actions and sometimes we're doing random actions. So this is just a step of a sample experiment where on the y-axis, we have the average reward, right? So as we do more and more things, as we learn more and more, ideally our average reward is going up, right? So we are picking the best slot machine more and more. So here we have epsilon equals 0. this graph, if we never explore, then we're never really going to learn anything, right? So we stagnate very, very, very quickly. If we choose epsilon equal to 0.1, it turns out that 0.1 ends up being a great learning rate. So you just set it like, we're going to move 10% towards our goal every time, towards our target every time. What you'll see with epsilon equal to 0.1, which is 10% random, that we're going to learn pretty quickly, right? We're going to learn pretty quickly. However, we still have to realize that 10% of the time we're doing a random action. So that's hurting our overall random reward. So if we lower our epsilon, for example, we could say set epsilon equal to 0.01, so 1% of the time we're exploring. You'll see that if with a lower epsilon, it takes us a lot longer to learn because we're not exploring as much. But once we do learn the values, we don't want to explore very much, right? So once we've tried everything a million times, we're very sure, so maybe we don't want to explore a lot. So the point of this graph is to show you that high values of epsilon learn quickly, but they still explore a lot. Low values of epsilon learn more slowly, but they choose the best value more over time. So it may take longer to learn with a lower value of epsilon, but in the long, long run, you'll probably get better rewards overall. This is also an interesting graph, which is, instead of plotting the average reward, this is saying, how often am I picking the optimal action? Well, if I have epsilon equal to 0, then maybe I get lucky, I pick the best action, maybe I don't, because I'm not exploring, right? So on average, I'm not picking the best option very often if I'm never exploring. Here, we can see that epsilon equal to 0.1 is learning over time which is the best action to take. But if you think about it, as this graph goes up and up and up, this is going to plateau at 0.9. Why? Why is it going to plateau at 0.9? Well, it's because if we have epsilon saying 10% of the time choose a random action, then 10% of the time we are not going to be taking the best action, right? So we could never get to 100% of the time always choosing the best action if we are still choosing other actions 10% of the time. But what we see here from epsilon equal to 0.1, it takes longer to learn which is the best action. But eventually, once we do learn it, then we'll only be choosing random actions 1% of the time. So as time goes on, epsilon equal to 0.1 will be choosing the best action more often. And so it actually turns out that what some people do in some algorithms is over time, they start with a high value of epsilon, and then they actually reduce the value of epsilon over time. We won't go into that just right now, though. I just wanted to mention it. But what these graphs are trying to say, you should understand that for an exam, okay? The fact that lower epsilon learns slower, but eventually produces better results. Okay, but that eventually may be a long, 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 long time. So you generally don't want to choose 0.01. So now we have all the tools we need to implement our Bandit algorithm, okay? So what's going to happen is the following. We're going to choose a value update method, whether it's the sample average estimate or the incremental update. Then we're going to choose a action selection method, whether that is greedy, epsilon greedy, whatever. So we're going to choose these things. That's the basis for how we store and choose actions. And then the process repeats. We choose an action to perform, we get the reward from the action, and then we update our value estimate for each action. And then that just repeats. Pull a slot machine, see what we get, do the math to update our value, choose an action, see what we get, do the math to update our value. That just repeats forever. So here is the pseudocode for that. Say we want to do incremental average with epsilon greedy action selection. So here is our Bandit algorithm. We've got some number of bandits there. So let's say that this bandits, that's like an array of slot machine objects or something like that in our code. So our initial Q array is going to be all zeros, and it's going to be equal to bandits.size. Now, this is not valid JavaScript, okay? Don't try and write this in your assignment, because some people do and then ask me, it didn't work. This is not JavaScript. It is pseudocode. N is going to store the number of times that we have chosen each bandit. That is the one thing we haven't talked about so far. I need to tell you you need to keep track of not only t, which is the current time step. So the current time step is how many total pulls that we've done, but we also need to keep track of how many times we've pulled each individual bandit. Okay, so that's what n is. Then, while true, we're going to say action equals null. That's where we're going to store the best action. And we're going to generate a random number between 0 and 1. So rand here generates a random number between 0 and 1. If that is less than epsilon, right? So again, this is how you deal with like random firings, just like in your GA. We have epsilon equal to 0.1, for example, so 10% of the time. If we generate a random number between 0 and 1, then 10% of the time it's going to be less than 0.1. So if random is less than epsilon, we're going to grab a random action. Otherwise, if it's not less than epsilon, then we're doing greedy selection. So our action is the action which maximizes Q of A. So we look over Q of A and we find the maximum A. Then we get our reward, and the reward is, hey bandits, whatever, however that's implemented, we look up in the bandits array that action index and we get a value. So that is just me. If my best action was 3, I look up slot machine 3 and I pull the lever. That's what happens. Then I'm going to increment the number of times that I've chosen that action. Then I just use my formula. So my new value for Q of A, so A here is action, right? So A is action, is the old value of QA plus, and this is the incremental average formula. So it's 1.0 divided by the number of times that we've chosen that action times R minus Q of A. That's it. Like, it's just what we said. It's a pretty easy algorithm to implement. Okay, so I mentioned before how in these graphs, what some people do sometimes is put epsilon down over time. But can we maybe do something better than that? And it turns out that someone did find something better than that. That is called the upper confidence bound. So exploration is needed because there is uncertainty about the accuracy of action value estimates, right? So we need to explore in order to reduce our error in our estimates. Greedy looks good now, but it might not be the best in the future. Epsilon greedy explores, but it explores randomly. So what would actually be better is if we select among the non-greedy actions that may be close to optimal with some measure for how certain we are about their values. So essentially, choose an action which looks good, but we want to have some measure of certainty when it comes to that sample, okay? So we're not just choosing something at random, we're being selective about it. And the UCB selection method does this. Here is the UCB formula. I'm going to disable my camera because it's up in the top here. So I'm going to go over all of these terms right now. So the action at time step t is equal to the action that maximizes this value. Okay, so what the hell do all these numbers mean? Well, ln of t, that's the natural log of t, that is the total number of time steps. Nt of a is the number of times that A was selected. C, which is greater than 0, is a constant that controls the degree of exploration. And typically what we do in UCB is we try every action once before we use this formula. The square root here is the uncertainty of a value estimate. So this has to do, it's the same function as the variance. And the function calculates a sort of upper bound on the possible true value of A. So what this does is that as NT of A increases, the uncertainty goes down. When t increases, but not nt of a, the uncertainty goes up. So all that being said, here's kind of what's happening. We take our old value estimate for an action, then we're going to add this term. As we pull an individual slot more and more and more, this value here goes up, but it's in the denominator, so this, the uncertainty, goes down. This is a measure of uncertainty. But as we pull other things more and more and more, relatively, our uncertainty about this action goes up, right? So if we have pulled this slot machine 10 times and we've made 20 total pulls, relative to other things, I'm quite certain about this one, about this A. But if we've pulled other things 1,000,000 times and only pulled this one 10 times, then I'm very uncertain, right? And so this C here is just a constant. If you put C way, way up, then it will explore very often. Typically, C is going to be a value like 1.5, 2, 3, something like that. And it's just saying, if we are uncertain about a particular action's value, we should choose that thing more often in order to reduce our uncertainty about it. Okay? So here's what we get. We get UCB with C equal to 2 as we go more and more often. As we pull more and more slot machines, we are going to be exploring less and less and less over time, but it will explore and figure out the true value just like epsilon greedy. So it's a good algorithm. Let's just say that. Okay, let me put my camera back on. Cool. Now we have to talk about QA versus Q of SA. So Q of A is what we've been talking about so far. There's just a bunch of slot machines in front of us, and it's our estimate of the value of doing action A. The value of a specific action, though, might vary depending on the state that it was issued. For example, moving up might be really, really good if our goal is above us. But if the goal is below us, then moving up is bad. So what Q of SA says, it's the value of doing action A at state S. Okay? So here's what that looks like in our pathfinding, for example. So we've got our pathfinding system. You're very familiar with this by now. At some point, we've got, at a state, we have a number of possible actions, right? So at each state, we are going to keep track of the value of doing each of these actions. Going up is just like a slot machine. We're trying the value of going up and seeing what it gives us. Going left is like a slot machine. All of the actions we can do at this state are like slot machines, right? So our values of QSA are, well, the value of QS up is going to be our estimate of the value of going up. QS1 might be down, QS2 might be left, up, down, left, and right, for example. But at this state, it's going to have its own value estimates of going up, down, left, and right. This state, it's going to have its own value estimates of going up, down, left, and right. So everything we've done so far with the n-armed bandit problem, that is actually going on in every state of the environment. We are keeping track of our state action pair estimates. So to sort of wrap, so this is what we're going to be doing on assignment 5, is we're going to be learning an algorithm that helps us update our state action value pairs and then choosing an action based on that. So to finish off this lecture, sometimes I do this. What are some possible exam questions from this? Well, the formula for the average and the incremental update. Be prepared to do an example like I did in the slides. You've got to know what exploitation versus exploration is and be able to define that and give examples of that. Action selection methods. So we've got greedy, epsilon greedy, UCB. I will not ask you for the let me rephrase that. If I'm going to ask you about the UCB formula, I'm not just going to be asking you to write the formula. I'm going to give you the formula. And I'm going to ask you something about the individual parts, like why does uncertainty go up if this value changes, etc. And the effect of epsilon as it goes up or down. So for example, if we have a high value of epsilon or a low value of epsilon, which learns faster, which explores more, and the overall Bandit algorithm and the pseudocode that I did. So that's it for today. That is the lecture. Let me go back to here. In the next lecture, we'll be talking about Markov decision processes and dynamic programming. So we can tie this all together with like the fancy definitions of MDPs that are out there in the literature. And that's it. So that's the math of how we're going to be doing this stuff. And reinforcement learning algorithms, or RL methods, are just slightly different ways of choosing which action that you want to do and updating your values. That's it. So yeah, that's it for today. And I'll see you in the next one.